I am a aerospace engineer and working now in the Chilean Air Force. And well, my idea today is present you a review of the state of the art and of the in-space propulsion for small satellite market. We are very interested in this area of the space technology because in here we are started with a new space program that is very revolutionary here in Chile, in my country, because we are really started in the, and we are initializing with the develop of our own systems. And for this reason, we are interested in the developing and test this new technology. We are starting building some our national laboratories, for example, and we expect that in the next 2 or 3 years build our satellites here in Chile. So for starts, I try to develop a schedule for this presentation. I will try to take this topic, some definition for speak the same concepts or clarify the concepts. We try to define or try to understand the context of the small satellite market. We will review some application for this. Finally, we are talk about the propulsion system for small sat, and we are conclude with some topic and some ideas. Okay, so for definitions, it's necessary to establish what is what is the idea of the small sat. So there's different authors that define different limit for the small satellites, but if we are based in the NASA report that is cited in this slide, it's possible to see a clear definition or limits for the small sat. In this case, the NASA defined the 180 kilograms. Sorry, and this idea is very interesting because in the future we will see that there are some limitations in the propulsion system for all this range of satellites. Okay, having this definition, we are review a context of the small satellite market. For start this review, it's necessary to see what is the evolution of the small satellite launchers, or how is the history of this launch. I use for this analysis the UCS satellite database, and here it's interesting to see. Sorry. Exponential growth of the launch in the last 10 years, more or less, that but with a concentration of launcher in the range of the 120 kilograms. If we think in the future, for example, it's possible to make some exercise. I perform this exercise now, and I try to perform a linear regression with this data, and we can see that, in the future we can see that tends to build satellite more and more lighter. So this is important because the satellite propulsion system, we need to consider the mass of launcher for this satellite. And for this data, it's necessary to take some precautions because these reductions are influenced by the satellite positioned in this part of the spectrum of the small sats. And this part of satellite, the femtosatellite, have a very special condition because how we will review in the future of this presentation, they are not propulsion system in the market that supply the need of this segment. So this is very interesting because this satellite have a very big problem for the operators. All my career are related with the at this moment are related with the advising the operation of our satellite. So all these satellites have more and more advice for collisions, so more and more message for collisions. So it's necessary to think in a way to give to this segment of the small sat the capability to maneuver on the orbit. Okay, if we review, for example, what is the mission or the common mission of this satellite that I use for this chart, the SIME database, is possible to observe that there are a very big concentration in two kind of missions, the communication and air observation mission. And this is very interesting because, for example, these two missions have difference needed for the operations and have different needed for the, when I say the operation in the orbit. So I say, for example, some mission need to position and point in the satellite for fulfill the mission. And in this, I talk about the air observation and communication, for example, have the needed to, if we think in the Starlink constellation, for example, pass from the orbit of the orbit backup orbit or backup orbit satellite to operation orbit. So if we review also the mission, and if we think in the segment of the CubeSat, or for example, it's possible to see that there are very big gap in the system with small sat with propulsion and without propulsions. This gap is close to is over the 90%. So this is very important to consider that this satellite that could be dangerous for the operation of in the space environment, needed the capability to perform some maneuvers or perform some corrections for fulfill the mission, or perform maneuvers for avoid some other object in the space. Other important aspect to remark this idea is what is the preferred orbit for these small sats. And how we can see in the slide, the majority of these satellites prefer or are designed for the orbit, for the LEO orbit. So we are overpopulated orbit for this kind in this moment, and we need perform a lot of maneuvers. For example, in my case, I operate the satellite as a Charlie, the SSOT satellite, and we receive for month more than 100 satellite collision message, and we need to analyze this. In the more dangerous case, we need to analyze the possibility to perform some maneuver and correct our orbit and avoid some collisions. Okay, taking in mind the context of the small sat market, is needed to a quick review of the application for the satellite propulsion system. Often is we have four main tasks for say of the satellite propulsion system. I take this concept for the SMAT of Larson and Wertz. We can when we think in the satellite propulsion application, we need to consider first of all that depending all the systems depend strongly of the mission defined for the satellite, and with this mission, we can project what is the requirement defined for this satellite propulsion system. For review this figure, it's necessary to consider that one propulsion system will be used, for example, for station-keeping maneuvers, for anti-collision maneuvers, for inclination maneuvers, and finally, I named this concept the final orbit positioning. When I talk about this concept, I think in the idea to change the orbit of this new constellation, like OneWeb or Starlink, when we have one orbit to backup of all my system, and then we need to position this satellite in one operational orbit. Okay. With this concept clarified, when it's possible to move forward to the propulsion system for the idea to characterize the propulsion system. In this case, it's necessary to mention that the concept that the data that are available for the propulsion systems is very it's not so much it's not available for decide what kind of satellite or what kind of propulsion system is better for my mission. So because there are not a lot of information for this system. So because this problem, due to this problem, the NASA proposed a new way or a new paradigm to characterize the systems, because when we need to characterize some system, immediately we think in the TRL scheme, but in this case, not possible because there are not some information. So the NASA proposed the PMI concept, that means progress toward mission in function, and group the information or group the propulsion system in one of these four concepts. The first one is the idea of is a classification of concept, is named C. This means that the propulsion system is an idea, is a feasible, and might be in this case include experimental data to support the physical validity of this idea. If we have a satellite propulsion system that is classified with C, this means that it could be in a range of TRL 1 or 1, 2, 3, more or less. This is the idea. Okay, this new paradigm not replace this concept of TRL, the TRL characterizations. So this new paradigm define a new tool for for characterize this propulsion system. The second one is defined with the letter D, meaning development, and group the system that have a low fidelity. So they are devices with a low fidelity operated in a controlled ambient like laboratory. But the main characteristic of this concept is that they are not mission defined for this propulsion system. So, and in the other side, we have the letter E, the engineering to fly concept, that is similar to the previous one, but in this case we have a mission defined for this propulsion system, and maybe there are a team of researchers dedicated to specifically characterize and design this propulsion system. This is the main difference in between the D and A. Sorry, D and E. And finally, we have the concept of the flight demonstrated, name it with the letter F. And in this case, the device has been successfully proved on mission. This could be in the range of 7 to 9 in the scale of TRL. And the definition says that this successfully proved mission could be a mission that fulfill the 100% of my requirement, or maybe we fulfill, I don't know, 60% of my requirement. So the main idea is not the proved technology that full all the complaint, all the perform. That the idea on this for the letter, the classification F, is that the system will be proved in flight. This is the main idea. Okay. Traditionally, the standardization of the propulsion system follow this schema, this graph, or this figure, sorry, and we can put all our system in one of these groups. So for example, electrothermal, cold gas, cold or warm gas, hydrazine, and so on. This is the main idea. We can find this in all the literature. Some authors like Kresic and Lozano propose this study, this paper, that they characterize some propulsion systems and point this propulsions in some of the group that we see previously. But in this case, we can see what is the level of maturity for this technology. So following this development, I take the data from the NASA, and and in this case I plot all these this case. Okay, I plot all this propulsion system in this chart, and we put what is the level of maturity for each one of the propulsion system that are collected by the inform of NASA. In this case, for example, well, you can see the red one mean the flight demonstrator system. The red one is in the engineering to fly. The blue one is in developed system, and the black means that the system is only a concept. For example, here we have a point that is a hybrid chemical propulsion system that in this case is only a concept. And on the other hand, for example, we have here a system that is a propulsion with the technology Hall effect propulsion thruster that is have the condition of flight demonstrated in this case. But we can analyze deeper this graph, example, and we can put we can group this propulsion system in the groups that is often showed by, and we can find in all the literatures, and all the propulsion systems have grouped in this main in these areas that is usual to see. Okay, if we analyze deeper that I say previously, it's possible to see, for example, that here we have a propulsion system of hydrazine, chemical hydrazine, and we can see here that all the systems described by NASA have the higher level of maturity. This is the main point. But, and I'm sorry, no, but on the other hand, we have here what is the mass of this satellite, this propulsion system. And we need to consider also that this mass consider not consider the fuel. The fuel is a dry mass of the propulsion system, and there are and in this case we need to consider for the application in the in our satellites. Okay, following we can see, for example, the monopropellant or bipropellant propulsion system. We can see in the left one we have a detail of the specific versus thrust, specific impulse versus thrust, and we can see what is the level of maturity of all these propulsion systems with their level of maturity. So, and I put here what is the fuel that these systems are used. What is interesting of this graph is this area, because in this area we have the more quantity of propulsion systems with a high level of maturity. So maybe if we need we need to use a propulsion system of this with this technology, is important that consider that our level or relationship thrust specific impulse will be in this area. Other important characteristic like the previous one is the mass of this propellant, and we can see that there are important increase of the mass of these propulsion systems. So they are propulsion with for example, lower 1 kilograms, but there are other technology like this one that is very that's a weight very high. So it's important to consider that, because, for example, maybe it's not a good idea use this technology for a satellite like I don't know, satellite CubeSat with 12U, for example. It's not possible because we don't have we'll have space for other payloads, or for payloads. Okay, in this case, we can see the hybrid chemical propulsion system. It's important to note here that for this technology, this kind of technology, we don't have a high level of maturity. Okay, this we have here with a very incipient level of technology. Next one, we can see the cold wash system. In this case, the more important of this technology is a very, very proven technology. That is possible to see with the chart of the left chart, because we can see, for example, all the systems are marked with red. We can see that there are a lot of alternative of fuel for our system, and it's a very, very important. But the constraint is that we have here a low level of trust for our system and specific impulse. Other important thing for this one is the idea, the mass of this product, that is lower than the previous one. That is possible to include this system on, for example, cube submissions. But it's necessary to consider that for perform maneuvers with this kind of the propulsion system, they are not to maneuver, or we need a lot of time for perform this maneuver. So there are some complication with this idea, because, for example, when it's needed to perform anti-collision maneuvers, in our case, with I work every day, and we have performed maneuver with 72 hours of anticipation. This is the better time to perform a maneuver, and the cycle of activities. Then we have subscribed with the 8th Space Squadron of the United States. So they inform to us when there are some object that could be in trajectory of collision with our satellite, and then we recompute the ephemeris for this object, and with this compute we inform to this if it's necessary we simulate a maneuver, and we inform to the United States what is the new ephemeris with the maneuver, and if there are not complications with others objects in the space, we execute this maneuver with our satellite. So all this cycle of activity involves 72 hours. So and we have a propulsion system of hydrazine. So for use this kind of technology, we need more time for perform this maneuver. In this case, we need to think in a new procedure for doing this kind of space operation. Okay, finally, we can see the solid chemical propulsions, and we have also here a system with a low level of maturity. The electrothermal electric propulsion, there are a lot of system propulsion here. One important is there are some technology with a high level of maturities, and we have here for this category a high level of trust and high level of relationships specific impulse trust. But we have here a system with a low level of mass. So with this technology, it's possible to think in maneuver for satellite, for example, for CubeSat, for example, but with the same restriction and same consideration that I mentioned previously. The same case with the electric propulsion here, which is important for my organization, because the satellite that we are designing use this kind of propulsion systems. They are very had a high level of maturity and have a lot very low mass propulsions. It's a very low mass for each propulsion system. The same way for the ion propulsion system, the effect hull here is a very interesting case. They are a system with a low mass and a very high in this area of the maturity levels. The pulses plasma, they are very low. There's a very important opportunity to develop in this area. In conclusion, or finally, we can see that there are some part of the range in the small sat definition that is possible to use more of the propulsion system described previously, but there are a part that we don't have propulsion system for this satellite. So we need to, it's an opportunity to think new researches in this area. Finally, in conclusion, there are not sufficient information to characterize a propulsion system under the TRL concept. For this reason, this proposes the PMI scheme due to the definition deficit of information. The mission definition always is very important to remark. Always a key factor to select selection proposed. There are different propulsion systems that could be can be used for different operations. This is important because if we have a bigger satellite, it's possible to select 2 different propulsion systems with a compromise the mass of the satellite. Also, depending on the platform, it's possible to include more than 1 propulsion system. And finally, the electric propulsion system keep a high potential for growth and development, considering in this case we will see previously the miniaturization of the platform. This is all for me. Thank you very much for your attention.
Perfect, Emmanuel. So thank you for the presentation. Obviously, it was very interesting, and what you provided, again, the different option for in-space propulsion and how their use cases are. So that's very important. So just one last question before we go. So how do you see basically the most promising applications for the small satellite propulsion systems, and how do this compare to the larger spacecraft?
Okay, for the first one question, and consider the miniaturization of the technology, I think that the better idea is or the better opportunity are in the electric propulsions, but considering that it needed to find new ways to take information about what is the other object in the space, because if we have the opportunity to perform satellite more lighter with a miniaturize the systems, we can include the electronic propulsion, but we need more time to develop maneuvers, operation maneuvers in the space. So this constraint that could be very collisional idea need to be rethinked. We need to review how we develop the process that perform space operation for example, correct the orbit, station keeping correction, for example, in the space. How we rethink the process of anti-collision maneuvers in the space using in my opinion, the better option that is the electric propulsions.